In this second quantum mechanics lecture, we're going to get into a little bit more about what quantum means, and we're going to use an example of polarized light. So if you've seen a movie in the last decade or so, you might have seen it in 3D, and you'll be familiar with the idea of polarized light being that, if we polarize light, we can filter it so that only one image goes through a filter and the other image goes through another filter. And therefore we can send different images to two different eyes and create a 3D effect. It's a trend that comes back every decade or so, every few decades, and it's probably ran its course. And it'll come back into fashion in another few years when the technology changes again. But anyway, that's what the use of polarized light is. But its use in quantum mechanics is because we can relate it to something called probability. And probability you may be familiar with from maths already, but it's really important in quantum mechanics itself. And once we've covered that, we'll briefly cover the idea of changing your basis. We covered basis at the very end of the first lecture. Now we can realize that actually it can be a bit arbitrary how we choose the basis, and if we change our perspective slightly, well, we can make the maths a little bit easier. So let's cover polarization. We know that the electric field is a vector field, and light, a light wave, is an oscillation of that field up and down over the course of space and time. So there's no physical wiggling up and down here. This is just the direction and the magnitude of the field. So there's no movement, it's just the field. But the direction is sometimes a bit arbitrary. And for most light sources, it's quite chaotic. It can't agree which direction that field is going in. So we use a polarization filter, and that can be as simple as a couple of lines etched into some glass. And what this filter does is it takes any energy that's oscillating in that direction and it absorbs it. It gets rid of it. So out to the other side of the polarization filter, every photon of light, all the light, agrees on which direction in the field it wants to oscillate in. And we can get some very interesting effects if we start chaining polarization filters together. So on the left here, we have our chaos. Nothing agrees on which direction the field needs to oscillate in. After the polarization filter, all agrees. It's going up and down. But this second filter here will absorb any energy moving in the up and down direction. So if all the incoming light is in that direction, nothing passes through, there is no light intensity. And if you take two polarization filters, put them at a 90-degree angle, it goes into extinction. No light fits through it. Things get a bit more interesting if we put them at an angle. So on the left here, we have our light chaos. It doesn't really agree. And after here, it's oscillating at 45-degree angle. So that's a little bit hard to draw and visualize in 2 dimensions. So it's going back and forward at an angle. Here, half the light is oscillating in that direction, half the light is oscillating in that direction. So this polarization filter is going to remove all of that light in that direction and leave us with just a small amount coming out here. And the light intensity has been reduced by about 50%. So here this is 100% intensity, only half the light makes it through that filter. Adding in a third filter, well, that makes it even more interesting. Again, we've got the chaos here, it doesn't matter which direction. Then it comes through 100% intensity. The 45-degree filter here is going to filter half of it out. And then half of it's going to be filtered again. 25%. That makes some sense. Each time we are removing all the energy in a particular direction. Now that effect is more complicated and weirder than it first appears, because if you were to remove this middle filter, then, well, we've got this and this are at 90 degrees to each other. No light would fit through. So we're actually allowing 25% of our light-ish to get through just by adding this filter into the middle. And when we start appreciating this in terms of quantum mechanics rather than just light waves that can be any value, that gets quite strange. I will drop in a few additional videos you can watch in the additional information below. So if we turn our perspective along to face along the path that the light is traveling in, we can begin to look at how the idea of vectors and a vector basis helps with this, because our electromagnetic field is oscillating back and forward in that direction, and we're just going to represent it with an arrow, a single arrow pointing here. And we can split it up into the x and y directions, and again, that is a theta there, an angle. We've got some kind of sine and cosine that we'll come back to that we can use to quantify this amount. So if that length there is our vector in the x direction, sorry, that squared is the intensity of light that fits through. The remaining intensity of light on that side is absorbed. So that's how we break vectors down into their basis components, and that can help us understand how much will pass through a polarization filter. Now we're going to switch to a quantum mechanical view of all this. So this is just, previously we're just assuming that light is a wave, it oscillates up and down, and the energy in a particular direction is absorbed by the polarization filter. In a quantum mechanical view, that's not quite the same, because we have to consider light as a particle. So a photon of light can be considered as a point particle or a tiny little ball, however you want to visualize it. It can act as a particle. It can still be polarized, but instead of thinking of it as oscillating in the field, here we need to think about it. What's the probability that it will be blocked by a polarization filter? So this is where we need to talk about probability and chance. We can't necessarily predict whether something will pass through this polarization filter, but we can say it has a 25% chance or a 50% chance, for instance. So let's think about it. All here we have photons traveling through at any particular polarization, and some will pass through that first polarization filter. They will agree that they can pass through the first. But there is a 0% chance that any of them will pass through this one at 90 degrees. They all agree that the field is oscillating in that direction. Anything in that direction gets absorbed. 0% chance of passing through. If we go back to the angled version, obviously on the left here we have lots of light coming through. These then all agree that they can pass through here. But on this side, only about half of them do. So it is a 50% chance. Each of these photons are effectively identical, but half of them are blocked by the polarization filter, half of them are let through, and that is completely random. We can't tell in advance which photon will be let through and which one won't be. That's the weird part of quantum mechanics, but it is predicted by the equations, and the next couple of lectures are going to be unpacking the equations that predict and describe that. Now we're going to look at adding some actual numbers to this and working out what those probabilities of things passing through a polarization filter actually are. So let's look back at this diagram again. We have an angle that the vector of the magnetic field or the electric field is oscillating at, and if we project that onto its basis set or its basis vectors in the x and y direction, we can see some right angle triangles. So if you're happy using SOHCAHTOA or something like that, you can probably work out which one is going to be sine of that angle and which one's going to be cosine of that angle. But another way to remember it is, if we think of that angle increasing, then a sub x in the x direction is going to decrease, whereas in the y direction it's going to increase. So if we look at our two trigonometric graphs, for instance, sine and cosine, well, the sine is the one that increases, so that must be the y direction. The cosine is the one that initially decreases, so that must be the x direction. So here, this must be cos theta, this must be sine theta. But sine and cosine of that angle don't give us a probability directly. we have to square square those values in order to get a probability. And there's a couple of quick justifications of that coming up right now. If we took sine 45 degrees, for instance, well, that is equal to 1 over square root 2. Now, if we take cosine of 45 degrees, well, that is also equal to 1 over square root 2. If we add those together, that's actually less than 1. So that implies some photons must just magically disappear. If you have a less than half probability of them being absorbed and less than a half probability of them passing, you've got a remainder left over. Plus, we know previously from experiments, if it's at that 45 degree angle, the light intensity must drop by a half. And 1 over square root 2 is not a half, it's less. What we can do though is square those values. Let's square both of them. Now we get a half and a half. Add those together and it's 1. So if we square that sine or cosine value, we square these amplitudes here, we get probability. And it also just so happens that cos squared plus sine squared is always going to equal 1. So that's a really useful way that trigonometry maps onto quantum mechanics. If you can get your head around trigonometry like this, quantum mechanics and splitting things up like this becomes quite easy. So let's have a look at the probability view of this. Here we have a set of photons. They don't agree on which direction they're coming at, but some of them will pass through anyway. So about 8 there. 4 will pass through here because it's at 45 degrees. And again, we've got another 45 degree offset. 2 will pass through. But if we're thinking these of just, does the photon want to pass through a filter rather than any kind of polarization, we get a little bit of a paradox, and the supporting videos I've added underneath will go into this in a bit more detail. But if we remove this filter, this then drops down to 0. And the interpretation of that is that these photons are only deciding whether they can pass through a filter when they meet the filter itself. Beforehand, we know nothing about their state or what they can do. It's only when they pass through the filter does a decision get made by them, which is a very weird way of thinking about it. This almost doesn't make much sense, but it is what the equations do predict. Now I'm going to briefly cover a choice of basis, because the choice of basis we have is arbitrary. So in this case, where we have two filters at 90 degrees to each other, it's quite obvious we can choose the basis in the vertical and the horizontal directions. And it's quite easy to figure out, will this pass through one of these filters by projecting them back onto the x and y direction and working it out from there. But if things are slightly more offset, well, it's a bit more difficult. Will this photon pass through this filter at 45 degrees? Well, that filter is 45 degrees maybe. We have to project onto here. That's a bit more of a complicated operation to do. But there's nothing special about the horizontal and vertical direction in this. Why not just change those axes to be 45 degrees and match the polarization filter? Then all we need to do is, with a single angle, project onto the right basis. That's much easier to do. And now we're not going to cover too much more of the maths of how to swap these bases. We just need to know that the choice of perspective we use changes how we describe things. But all these perspectives that we can have are also valid. We can set this basis to be any direction we like. The only factor is that these must be 90 degrees apart. They must be orthogonal. And the idea of orthogonal basis vectors or basis states will become really important later on, especially in computational chemistry. So that brings us to the end of this second lecture. We are doing polarized light, so we can talk about filters. There's also linking it to probability. There is a probability that a photon will pass through a filter. It's not just a case of waves truncating to wherever they need to be. it is a yes/no question. And then briefly covered the idea of a change of basis. We can angle our basis vectors around a little bit to make the maths more convenient.